let's just go right to Prox gradient descent. This is what we learned last time. The problem that we're thinking about is minimizing a sum of two functions, g plus h, where g is convex and smooth. And h is convex, but it's not necessarily smooth. But it has a special property, and that property is that its Prox operator we know how to calculate, at least efficiently, approximately. You know, it's not just some black box when we go and apply it, but we actually know what this Prox operator is. So just to remind you what the definition of a proximal operator is, it depends on a function h and a parameter t. So sometimes we'll write it as prox of h comma t, but for this lecture, you know, we're just thinking of kind of the one function h being implicit that defines the prox operator. And it's defined as the minimizer of this problem, this strictly convex problem. You pass in x. With respect to this minimization problem, it's a constant. It's the value at which you want to evaluate the proximal operator. And we minimize over all z 1 over 2t times the 2 norm of x minus z squared plus h of z. So the unique minimizer of that is defined as the prox at the input x. Okay, and we saw that, for example, for the 1 norm, if h was the 1 norm, we already proved this several lectures ago. The answer was just soft threshold the elements of x by a certain amount. If h was just the 1 norm, it would be by the amount t. Okay, so move every component of x closer to 0 by the amount t, and don't ever move it through 0. Okay, set it equal to 0 if it's already within the interval minus tt. That's what the prox operator would look like if it's the 1 norm. And proximal gradient descent basically just makes a gradient step with respect to g, pretending like g was the only thing you had in the criterion, and then applies the prox of h to that. Okay, and this tk is the step size at each iteration. Notice that the step size that we take for the kind of inner gradient step with respect to g and the parameter at which we evaluate the prox operator, those are the same. Those are the same thing. It's tk. So changing the step size affects this update in two ways, right? It affects the length of the step with respect to the gradient of g, and also it affects the prox operator. So that was proximal gradient descent. Sometimes to make it look more familiar, we write it like this. As the previous step, previous iterate xk minus 1 minus the step size tk times something called the generalized gradient, where this guy is just defined so that this is nothing more than that. Okay, we just define the generalized gradient so that we can write it in this form. Sometimes it's helpful to remember it in this form because it looks like gradient descent, and this thing kind of behaves like a gradient in some ways, as you'll see on the homework. Okay, so just for our one example we went through last time, we went through what happens if you're, for example, trying to solve the lasso problem with proximal gradient descent. And in fact, this algorithm that we wrote down, it's not really specific to having a least squares loss. It would also work like a logistic loss or really any smooth convex loss. All that would change would be essentially the gradient. So as long as you can calculate the gradient of this smooth part, the loss function, let's say, efficiently, then the computational complexity of this algorithm wouldn't really change. So just to remind you, we worked out that we reminded ourselves that the prox operator of the 1 norm was just soft thresholding. And in fact, if we have lambda times the 1 norm, then the prox operator is soft thresholding at the level lambda times t. Okay, if the prox operator is being evaluated at the parameter t. And so proximal gradient descent, right, it just took a gradient step with respect to the smooth part of the criterion, which here our optimization variable was beta, and the gradient was minus x transpose y minus x beta. That's just the gradient of the least squares loss. So where we're moving initially is beta plus t x transpose y minus x beta, and then we apply the prox operator to that. We just take that thing, and we look at all of its components, and we set them equal to 0 if they're small. Otherwise, we move them closer to 0 by the amount lambda t. Okay, it's nice. It's very simple. It's very fast, these iterations. And it also kind of gives us some intuition as to why we get sparsity in the lasso problem, right? Because we can see we're actually constructing the solution through this algorithm, and this algorithm will be setting things to 0 either whose components were small in the previous iteration or such that the gradient didn't push them too far away from 0, right? As long as this thing isn't too big an absolute value, then we'll be setting it equal to 0, right? In particular, if it's less than lambda t in absolute value. And just think of this as beta minus t times the gradient of g when you don't have the least squares error loss, right? It's whatever other loss you're looking at. It's really the same sophistication in terms of applying this algorithm. Okay, and we just saw that in this case, actually, it's perfectly fair to compare this to, say, the subgradient method for the lasso, because Each iteration costs the same computationally in terms of, say, the number of flops. If we were to kind of carefully look at how expensive this is versus the subgradient method, the soft thresholding operator is very cheap to apply, right? And it's, an important point is that given that we've kind of leveled them, it converges much faster. It has a much faster convergence rate compared to subgradient method. Okay, and then the convergence analysis we just discussed last time. You're actually going to prove this on your homework. So this is question 4 on your homework, and the proof for this is kind of laid out in steps. Those steps, in some ways, very closely parallel what we did for gradient descent. So, I think that the question's pretty well written, and you can kind of, make your way through the parts. But if you're having trouble, go back and look what we did for gradient descent, and that might kind of provide you with some inspiration for how to solve the parts. So the setup is very similar. It's just that we're assuming that G is the guy that's smooth and has a Lipschitz gradient. Both G and H are convex, and H has a Prox operator that's tractable that we can evaluate. And it's essentially the same result, even up to constants, right? We get, after k iterations, that the difference between our function f at xk and the optimal value f star is less than or equal to the square distance between where we started and the solution, or a solution, divided by 2 times t times k. So in terms of the epsilon notation, right, how many iterations k do I need to take in order to make this less than or equal to epsilon? It's just 1 over epsilon iterations on that order. Okay? So same as gradient descent. The proof is even similar to gradient descent, but important caveat is that this counts the number of iterations of Prox gradient, and in some cases that will be kind of on par with how expensive a gradient descent method would be, but some cases it's not. In some cases the Prox operator could actually be expensive to compute. So this is just counting the number of iterations, but each iteration is a evaluation of the Prox. And we'll give an example of where that's expensive, I think, just in a few minutes. So where you should kind of remind yourself that we're talking about outer iterations of this algorithm, and it may not be kind of fair to say that this algorithm takes 100 iterations and another algorithm takes 100 iterations, because they may be doing different things on a per iteration basis. Backtracking was really very similar. We just essentially replaced the backtracking rule for gradient descent, where we saw f everywhere, with g. So I've written down a backtracking rule here that only operates kind of on the smooth part. In some sense, it just looks for sufficient descent on the smooth part of the criterion, and then it uses the generalized gradient in place of where you would have one appearance of grad g if you were to be doing, say, gradient descent on g alone. Okay, that's one way to remember it. There are other options for backtracking with proximal gradient that look for the entire function, f, g plus h, to descend kind of sufficiently at each step. I don't think, in my experience, they work very differently, and this one is just simpler. So you can just kind of remember this one for the purposes of backtracking. Okay? And something that we pointed out last time, just to write this out kind of a little explicitly, what we're really doing is we're saying, while this is true, we have to check whether or not, we've descended on the smooth part of the criterion. We're going to update t equals beta times t. So like, multiply t by 0.9, for example, shrink t. But what's hidden kind of in this description is that in order to evaluate the generalized gradient, we need to actually run the Prox operator, right? Compute the Prox. So, for example, let's say t was 1. I compute the generalized gradient at t equals 1. That involves evaluating the Prox operator, right? That was just this thing here. Okay, and then I check whether this is true. Suppose it fails. I get set t equal to 0.9. I have to go back to compute g at the parameter 0.9 of x. I have to go back and recompute the Prox. Right? The Prox changes each time I change the generalized gradient, which means that backtracking could be very expensive with proximal gradient if for some reason there's many inner loops needed before you quit this exit criterion.
Right.
Yeah.
The left-hand side, the x minus t times the generalized gradient in your notes there.
Yeah, thank you. This is the step you're going to take. We're thinking about this as a possible step. Thank you. Okay, there may be, I think that there are if I'm remembering properly, but I wouldn't want to write it down, chances of getting it wrong. There may be some approximate, even kind of rougher backtracking heuristics that don't require you to evaluate the generalized gradient each time, but just kind of keep the original generalized gradient and scale it down appropriately. I don't know how common those are. But if you're really looking to use backtracking and the prox operator is really expensive, there may be some kind of heuristics, or perhaps even more than heuristics, that you could run to get away with not evaluating the generalized gradient each time in the inner loop. I'm just not super familiar with them. So yeah, the conclusion, though, is that if we use backtracking, say this version, then we get the same rate. And in fact, the proof is still very similar. I don't think we have you do backtracking on the homework, but the proof for this is really very similar, just like the proof for backtracking in gradient descent was very similar to the proof for a fixed step size that was small enough. So let's do an example in which the prox operator is actually rather sophisticated, and the algorithm that we get out is kind of interesting, and that's the matrix completion problem. So this problem I don't think we've talked about yet in class. It's gotten a lot of attention in the last 5 to maybe say 8 years or so. And we could kind of abstract it out as follows. So we're given a matrix that's an n by n matrix, and we only observe some of the entries of this matrix. So let's call omega the set of indices that correspond to things we actually observe in the matrix. So we only observe yij if ij is in the set omega. And let's suppose we want to fill in the missing entries. And so the kind of canonical problem you could think of is something like the Netflix problem. So that's where a lot of attention was devoted to this kind of optimization problem, or just matrix completion in general. So think about yij as being a matrix where, let's say, the rows are movies and the columns are people, and I only observe some combinations of movie and people, in the sense that, let's say, for each person, some person watches some number of movies and rates them. I think that the Netflix scale is actually on a 7-point scale, although I may be wrong. So suppose this person watched this movie and rated it a 6, then he or she watched this movie and didn't like it and rated it a 1, etc. But of course, for every user on Netflix, they're certainly not going to have watched every movie. That would be kind of amazing. And so there's going to be a lot of missing entries in this matrix, right? In fact, it's over 99% missing. If you look at the original Netflix plies, most of the entries are missing. And we want to solve what's called matrix completion. We want to kind of estimate the missing entries in a way that's sensible, so that we can, say, for any given person, try to impute what he or she hasn't seen in terms of the rating, try to guess what they're going to be providing as ratings for movies they haven't seen, and then make a recommendation for a movie that we think that they would have rated highly as to what they should watch next. Okay, so that's the matrix completion problem. Several different algorithms for how to do that. One algorithm that's, in a sense, works quite well is this trace norm regularization problem. It's kind of like a version of the lasso that we've seen several times so far, but for matrices. So what we do is we have a variable b that we're trying to solve an optimization problem, and b is going to be essentially what we estimate for the missing entries. We're going to be paying attention to b on the entries ij that are not in omega. That's going to be giving us kind of our estimate of what, say, the ratings would have been for those things we didn't observe. And b is going to be chosen to minimize the following criterion. So we have the least squared error loss between, or the squared error loss between yij and bij, but only over the entries that are observed, right? Because we don't actually even know what y is. That's the point off of omega. So it wouldn't make sense to write anything else down than this. So this is just saying keep b close to the ratings that we have observed in terms of the squared loss. And we're adding to this lambda times the trace norm of B. Okay, so what this is doing in, say, some statistical sense is it's providing us with some kind of regularization on top of what would be an ill-posed problem otherwise. Right? If we didn't have this term, if lambda was 0, then we would just be setting B to be equal to y on the observed entries, and there'd be no restriction as to what we do on the unobserved entries, and it'd be kind of pointless, right? There would not be a unique solution, and it would not really make much sense. What we're doing here is we're asking to find something that's close to y in the observed entries, but this also is low rank. Okay, and this low rankedness is a form of regularization. You can think about it in some sense as a matrix is low rank. Suppose this B is an m by n matrix, but it really only has rank k. That means we can factor it as a product of two matrices, U and V, where U is m by k and V is n by k, but at V transpose, I guess we'll write it as k by n. So we can think of these as kind of latent factors that drive the ratings. So there are somehow, this kind of explains what we're seeing in terms of the ratings in the Netflix problem. So this is some motivation for kind of imposing low rankedness as a kind of regularization tool. Another way to think about it is to try to connect this to what we've already seen with the lasso. You can really think of the trace norm as being the analogy to the L1 norm, but over matrices. Okay, if I had a diagonal matrix, then the trace norm is just the sum of its diagonal entries, which is kind of like taking the 1 norm of a vector, right? If I think about the diagonal entries as being the vector. So this is, in a sense, approximating the rank of B, because the rank is just the number of non-zero singular values of B, this being the sum of the singular values of B. Okay, so maybe the analogy you can keep in mind is the rank of B, right? It's the number of times that I scan through its singular values and I count when they're non-zero. The trace norm of B, or the nuclear norm of B, is the sum of the singular values. Okay, it's the sum of the singular values themselves. And the analogy here is like, this is matrix world. This is a convex approximation to the rank function, which is non-convex. Just like in the vector world, you might think of as the analogy, the L1 norm of a vector B, right, being the sum of the absolute values of B versus the L0 norm of B being the, sum of indicators that each component is non-zero. Okay, this is why I'm claiming you can think of it as analogous to what we're doing, say, in the lasso, but for matrices. And this connection is kind of precise, right, when B is a diagonal matrix. All right, so that's the problem. We're trying to find a matrix that's low rank that approximates what we've seen well on the observed set. And it's convex because, well, this is just a quadratic, right? That's certainly convex. And this is a norm. The trace norm is a proper norm. We kind of claimed that at the start of the class at some point, and you can check some classic matrix analysis textbooks for that. But this is a norm, so it's convex. Okay, so this whole problem is convex. So how do we solve this problem? Actually, before people really started using proximal gradient, problems like this were pretty hard. In fact, this problem was especially hard. This is a semi-definite program. That's not very obvious to see, although I claim that was the case in the STP lecture. And maybe Javier, when he starts talking about duality in a bit, he might show you that connection, that you can actually prove that this is equal to, this is a special case of an STP. But we used to solve this with interior point methods, which are very, very slow for a problem like this. Proximal gradient provides us with a simple and also like relatively fast algorithm compared to the alternatives. In absolute terms, it's still much slower than something like ISTA, for the which is the this guy that we learned for the lasso. But it's still relatively, I think, a pretty fast algorithm for how difficult this problem is. So here's the way we set it up. We write down first some helpful notation, this projection operator onto the observed set. If you give me a matrix B, then I'm going to write P omega of B as another matrix, which just basically sets to 0 everything that wasn't observed. Okay, so it's just the projection onto the observed set, gives you back what you had on the observed set and 0 otherwise. So now we can write the criterion in a little more succinct form as the squared error. I mean, the squared term is just the difference between the projection of y onto the observed set and the projection of B onto the observed set. The Frobenius norm of that squared. So remember, the Frobenius norm of a matrix just takes the sum of squares of the entries. And this guy is now exactly just this guy, right? Because it's 0 on omega complement, and it's just exactly this on omega. So it's a nice, succinct way of writing the loss term. And we're going to call that G. It's smooth and convex. And we're going to call this guy H. Okay, this is lambda times the trace norm. It's convex because, well, I told you that the trace norm was a proper norm, but it's not smooth. Okay. So what are the two things we need for proximal gradient? We always need the following. Right? We need to be able to calculate the gradient of the smooth part and be able to calculate the prox operator of the non-smooth part. So let's do the smooth part first. That one's really easy. Notationally, it may seem this may kind of complicate things when you try to look at the gradient, but really the gradient is very simple. It's just equal to bij minus yij for all the entries ij that are observed and 0 otherwise. Right? Think about differentiating this element-wise for every element ij. Right? That first term there. It's just bij minus yij if ij was in this sum and it's 0 otherwise. Okay, so that's what I've written down here. Except I've just written it in this form because we're going to be subtracting off the gradient later, right? So it's helpful to have a minus sign here. So later we'll just add the gradient, or add this part. Okay, so that's the gradient, just what we just said. And the prox operator now, it is defined by minimizing over all matrices Z the sum of squared differences between bij and zij plus lambda times the trace norm of Z. So Z is the optimization variable here. B is the matrix at which we want to evaluate the prox operator. And T is the parameter for the prox operator. So we multiply this first term by 1 over 2T. So let's well, we either are going to calculate that or just kind of wave our hands a bit. I'm not sure whether it's worth our time to go through this calculation. So in previous years, we've done this in class. In other years, we've done it on the homework. To calculate this prox operator is really just an exercise in subgradients. So maybe we'll just, I'll just cite the results, and I think it maybe is better use of our time to focus on acceleration. But if we have time at the end of the lecture, I'll come back and give details. People are also welcome to come to my office hours and ask me about it. So here's the claim that the prox operator, evaluated at a matrix B, is a version of soft thresholding. So just like the prox operator for the one norm was vector soft thresholding, this is something that we're going to call matrix soft thresholding. What it means is that if you want to know what the prox operator is at a particular matrix B, then we take the SVD of B. So we write B as U times sigma times V transpose, where these two have orthogonal columns, orthonormal columns. And this guy is a diagonal matrix with positive entries. So this is just the usual singular value decomposition. Take the SVD of B. And then soft threshold the diagonal elements of sigma. Okay, so take each of the singular values and basically either subtract lambda off it and keep that if that's positive, or set that equal to 0. So this operation here is nothing more than just soft thresholding in the component-wise sense that we're already used to. The matrix sigma. Okay, so that's what the prox operator at the parameter lambda looks like. Soft thresholding the diagonal elements of sigma by the level lambda. So what this is doing, right, is this is giving us a low-rank matrix in return. That's something that you can also kind of use as some intuition as to why we're getting a low-rank solution out of proximal gradient, right? If B is equal to U times sigma times V transpose, and I write the columns of U as, say, U1 through, I'm not sure what notation I used here, if I had notation. Let's just call it R. Suppose that R is the rank of B times these diagonal elements. I think I called them sigma 1, 1 through sigma R, R. And let's say V, I'll just write it like this. Okay, so if this is B, then what I'm doing when I apply the soft thresholding operator to B is I'm taking U times the soft thresholded version of the matrix sigma. So soft threshold is diagonal elements, which we called sigma sub lambda. times V transpose, which means that effectively we're getting rid of a bunch of the left and right singular vectors. Right, let's suppose all we're able to keep up is to sigma kk, and then we set the rest to 0. Right, because let's suppose that sigma kk was the smallest singular value that's above lambda, and the rest are below lambda, so we set these all equal to 0. So then effectively, right, this is just taking essentially the first k singular left and right singular vectors. So it's giving us a matrix that is of rank k rather than of rank r if we've set, you know, r minus k singular value is not a 0. Okay, so that's somehow supposed to be giving us some intuition, just like we had with proximal gradient, that we actually do get a low-rank solution out of this algorithm, because at every step, right, we're going to be passing something into the soft thresholding operator, this matrix soft thresholding operator, and then we're going to be updating our iterate with the result of applying this, which is going to be low rank. So why is that the case? Well, this is the part where I think I'm just going to give you some high-level details, and then we'll see how much time we have at the end, or just punt, and you guys can come to my office hours or check the notes from previous years to get more details. So the way that pretty much we derive all prox operators, like you've done in the homework, is we just apply subgradient optimality. Right? You want to compute a prox operator, so you differentiate the, or you take a subgradient of the criterion, right? Set it equal to 0, and then find the value of z that makes that true. And here I've already told you what the answer should be, so we have to just check that we do get, in fact, a 0 subgradient of the criterion when z is equal to this. So it suffices, right, to check that if I take, you know, the criterion was this, are we doing it at the level lambda? I guess here I'm doing it at the level lambda t. So this is the criterion of the prox operator, right? And so I take a subgradient of this and set it equal to 0. So this part is smooth, right? And its gradient is just z minus b. And now let's just call a subgradient of the trace norm capital gamma. So this has to be equal to 0 for some gamma that's a subgradient, right, of the trace norm at z. That's what the subgradient optimality condition looks like. And we're going to have to check this when z is equal to, right, this guy. Where, you know, b had this SVD. Okay, so that's what we're going to have to check in order to check that the prox operator is indeed soft thresholding, matrix soft thresholding. Okay, so this is the main difficulty here is actually computing subgradients of the trace norm. So that's not very easy. So far, this has been kind of straightforward. This is the part that's not easy. And in fact, I can't remember if on the homework we had you guys do both directions. One direction is actually quite difficult. So it's possible to prove that, you know, subgradients of the trace norm are of this form. To prove that they're all the subgradients is actually a little bit more tricky. But here are the subgradients of the trace norm, say evaluated at the matrix Z. They are, if Z has the SVD, let's say U sigma V transpose, then the subgradients of the trace norm at Z are all matrices of the form UV transpose plus W, where W is any matrix that has the biggest singular value less than or equal to 1, and it's orthogonal to the columns of U and the rows of V. That's what this is saying. U transpose W is 0, and W times V is equal to 0. So these are all the subgradients of the trace norm at a evaluated at a matrix Z, if Z has the SVD U sigma V transpose. So one way to see this is the way we have you prove it on the homework, is to use the fact that, so to get subgradients of, say the trace norm, you can use the fact that the trace norm and the operator norm are duals. Something that is kind of a handy fact from matrix analysis. So in other words, I can take, if I ask what the trace norm is for a matrix Z, I have to look at all matrices, let's call it Y, that have operator norm at most 1. So these are things that have the biggest single value less than or equal to 1. And I just take, we've written this matrix inner product in a few ways. You can write it like this, Z dot Y. Okay, this means I just take the element-wise product of Z and Y and I sum it up. Okay, another way of writing that is like this. The trace of Z transpose Y. So this is using the fact that the operator norm and the trace norm are duals. And now you actually do know how to take subgradients of a max, right? That's something you guys know how to do. It's going to be the guys that achieve the max that have operator norm. So it's all the subgradients now are going to be all the matrices Y that have operator norm less than or equal to 1 that achieve this max, that have the property that if I take the inner product of that matrix in Z, I actually get the sum of the singular values, the trace norm. And in fact, you can just check directly. All of these guys will do it. If you take an inner product of any of these guys with this matrix, they're going to give you the sum of singular values of Z. And they all have operator norm at most 1 by construction. Okay, this has operator norm at most 1, and so does this. And these two things are constructed to be orthogonal. So that's the way you prove at least that all of these matrices are subgradients of the trace norm. To prove the other way around, to prove these are the only matrices possible that achieve the max here, it's a little bit more difficult. But it's not even needed for this application. For this application, all that we need to do is say that these are subgradients, and then we can already verify the subgradient optimality condition. Okay, so basically just plug this back in and check that we get 0 now that we know these are the subgradients. That'll complete this exercise. Okay, so that was done at kind of a high level, but I think it's probably better use of our time not to go through the details. And this is a rather tough prox operator. I mean, this is something that, the first time this was somehow realized to be tractable, it was considered like a cool thing and everyone wanted to use it. So this is not like a routine homework assignment. Proving this is the prox operator was, it was something that people didn't know, I don't think, at least maybe not commonly until fairly recently. So the prox operator, the trace norm is matrix soft thresholding. Okay, so now that we have that out of the way, we actually pretty much can put together our algorithm, right? Which is just take a step in the direction of the negative gradient of G. But that was really simple, right? The negative gradient of G was just, or this was the gradient of G. It's just minus Py, minus the quantity Py minus Pb. So if we take B and we add T times, and we subtract T times the gradient, then it's the same as taking B plus T times this direction, right? Py minus Pb. And we take that and we soft threshold it. And that's proximal gradient descent for the matrix completion problem. And remember, what this means is take the SVD of what's inside, and then kill all of the singular values that are smaller than lambda t, and subtract lambda t off of all the remaining singular values, and make a new matrix out of that. That's what applying this prox operator means. So before we just kind of discuss a bit more about how expensive that prox is, let's just note one other thing, which is that actually the gradient of our smooth part is Lipschitz continuous with L equals 1, right? This is the gradient of our smooth part was just this. This is just a linear function, right, in B. It's Lipschitz, obviously, with constant 1. If you just take the difference between this at B and this at B prime, then that's just the difference between, P omega at B and P omega at B prime. And that's going to be certainly less than or equal to, let's say, the Frobenius norm. The Frobenius norm of that is certainly less than or equal to the Frobenius norm of, let's say, B and B prime, right? Because we're just taking less differences when we're projecting onto the observed set. So it's definitely Lipschitz continuous with constant L equals 1, which means that we know from our convergence analysis we can take a step size in proximal gradient as big as 1 over L, which is just 1 here. Right? So this is another nice feature of this problem, that we have kind of the biggest step size possible we can take is easy to compute. It's just 1. And so plug in t equals 1 here. We get B plus, the projection of y onto the observed set minus the projection of b onto the observed set. So when t equals 1, our updates look like this, right? Soft threshold at the level lambda, because it's lambda times t usually, b plus p omega of y minus p omega of b. And look at this, b minus p omega of b. That's just giving us everything on the unobserved set, right? Because this has everything in it. This has just the things on the observed and zeros otherwise. So if we subtract that from b, we get everything on the unobserved set, which we're going to write as p omega complement of b. Okay, so this gives us zeros where we had observed entries, and it gives us bij where ij was not observed in the original matrix Y. Okay, that's what this is doing. So this is actually a very natural algorithm. We can interpret this as, at every step, I just look at my estimate, and I let that dictate what happens on the unobserved set, right, where I didn't see y's, and I just take everything that was observed for the original entries, right, that happened to be an omega. So this matrix just has yij where we'd seen them originally, and bij where we hadn't seen y's before. That's how we fill this matrix up. And most of these entries will be unobserved, right? So we're mostly filling this with entries bij. That's what this matrix is. Then we take that, we just make that low rank by taking the SVD of this and just soft thresholding a bunch of the singular values at the level lambda, and repeat that over and over again. Take whatever that gave us, call that b, plug that in for the missing entries, keep y in the original in entries that we had originally seen it, make that low rank again, take that, plug that back into the missing entries, and repeat. Okay, it's a very natural algorithm. In fact, this is sometimes called the soft impute algorithm. Right? We're imputing at every step the missing entries, and we're doing so in a soft sense because we're kind of at every point making the matrix have lower and lower rank by soft thresholding the singular values. And when this was proposed initially, it was not even realized that this was proximal gradient. This algorithm was proposed kind of on its own as a natural algorithm for solving this problem. And if you look at this paper, there's proof that this converges at the 1 over epsilon rate, and that it converges when you take exactly this form where you don't have a step size even. And only after this paper was written, maybe in a revision or 2 revisions or something later, the authors say, oh, this is actually just proximal gradient. So it's kind of an interesting coincidence. And I think that you could probably think the same thing about ISTA, right? ISTA is a very natural algorithm. You could think of that perhaps as something to do that you might have thought of on your own if you didn't know about proximal gradient for the lasso. So anyways, this is a soft impute, is exactly proximal gradient with t equals 1. It has all the properties of convergence we already know about proximal gradient. And it's pretty simple, and it's also pretty effective for matrix completion. Okay? So that's the gradient, right? So I'm claiming this thing is Lipschitz with constant L equals 1.
Yeah, right? I'm saying, what is the step that has to do with the Lipschitz?
Oh, that's always the case for us, right? For gradient descent and for proximal gradient, we proved that you can take the step size to be as large as 1 of the Lipschitz constant and guarantee convergence, right? That's kind of been the threshold, so to speak, that we know that we can always set the step size at least as large as that. Or at most as large as that, yeah.
So the L1 regularization is a reflection of our assumption that the matrix is sparse, right? Like the example that you gave for net
is the L1 regularization?
So let's just be a little more specific about nomenclature. So this is trace norm regularization.
Oh, sorry.
I had kind of said that it's like L1, but it's not exactly the same, right?
Right.
And that's actually more a reflection of the fact that well, I mean, it's needed because the matrix is very sparse. Otherwise, we don't really have many other options to estimate this matrix in a way that's kind of sensible. But the fact that we think about it as being low rank is more of an assumption about how we think somehow this matrix was generated. Okay, it's something more like this. So somehow we think that there are, let's suppose that, let's look at, let's say, the movies. There are really somehow k canonical movies, like movie types, like like action, romance, whatever. Pick k things, and somehow each of the movies in Netflix can be factored into somehow, some combination of those. Every movie you see is somehow a combination of like k prototypical movies, different genres, and then a similar thing you might be talking about for users, right? This is how each user kind of likes action movies in general, or likes romance movies in general. And what you're seeing is somehow this latent factor model. That's how these ratings we think are somehow being generated. So that's where the low rank assumption comes from. It's from a belief that somehow this is a reasonable assumption about the problem. But even if you don't believe this is a model, like even if, now we're talking kind of more about statistical modeling here, even if you don't believe this is a model, it's still useful to doing this problem because we don't have very many options, right? It's so sparse in the sense that we observe so little that we have to do something in order to make this problem well-defined, and asking for something to be low rank is just one useful way to regularize. It's a good question, though. Okay, other questions? So let's just spend a second talking about how expensive this prox is. This prox requires computation of an SVD, right? So it's very different than, let's say, ISTA, which requires ISTA soft threshold. It's a very different kind of order of complexity. A singular value composition is very expensive, especially when matrices are large, like at the Netflix scale. So we should be very careful about talking about iterations of prox gradient descent here and putting them on par with iterations of, say, another algorithm that just do like a matrix multiplication at each step, right? Because those are very different things. However, there are ways to compute this SVD efficiently. And that comes from the realization that at every step, look at what you're asking for the SVD of here. It's a sum of two matrices. This one is very sparse, right? Py of omega is very sparse. And this one, P omega, I guess here I called it P perp omega. In the notes, I called it P omega complement, maybe. Whatever that was, this guy. This matrix here is low rank. Okay, it's low rank by construction, right? At every step, B is going to be pretty low rank. And so we're asking to take the SVD of a sum of two matrices, one that's sparse, one that's low rank. It turns out that actually singular value compositions for the sum of low rank and sparse matrices can be done fairly efficiently using kind of specialized methods. More than that, we actually don't need to compute the full SVD. We just need to compute enough until we know that somehow the singular value that we're looking at, if we're computing, let's say, the singular values in order, right, with the biggest one and then the left and right singular vectors, and the second biggest one and the second left and right singular vectors, etc., we only need to compute kind of far enough along until what we see, the singular value we're looking at, is below lambda. Right? Because once it's below lambda, we know that essentially those don't matter anyways. Neither do their corresponding singular vectors, right? Because of this kind of picture, right? This matrix product, if we were to send all these to 0, is nothing more than just taking the singular vectors that corresponding to the singular values that survived. So you can kind of approximate, or you can kind of compute this SVD, this guy, efficiently, which makes proximal gradient for this problem even runnable on very large problems. But still, one has to be very careful. Okay, so it's just kind of worth pointing out. Yeah?
How different is this from PCA? Like, for example, if you run PCA first, because you're actually ranking basically in a way that you're avoiding the expensive computation by reducing the dimensions. So how is it different from running a PCA and then do this?
I mean, this is certainly related to PCA, right? So if I filled, let's suppose what I did at the start was I took my matrix and I just put zeros in, okay, where I didn't observe where I didn't observe ratings. And I took the SVD of that. That is already principal components analysis, right? Taking the SVD and PCA are like really one and the same. And I'm just, in this algorithm, we're just doing that repeatedly, and we're updating the missing entries at each step. But as I pointed out, and as you emphasized there, we don't actually have to take the full SVD, right? We only have to kind of compute enough of the SVD before we know that some of the remaining singular values will get shrunken. So in PCA notation, these are directions kind of in the latent factor model that represent low variation, right? These don't really contribute much in terms of the variation we're seeing in terms of the ratings. Okay, so we're just kind of getting rid of them and looking at only the high variation directions. Okay, so that was proximal gradient for matrix completion. So now we have good algorithms, solid algorithms for, I guess, two pretty common problems: the lasso and all the variants with different losses, and also trace norm regularized problems. Right? So proximal gradient is really quite useful for these types of problems. So let's look at some special cases of proximal gradient, and then we'll take a kind of our break. So proximal gradient is sometimes called composite gradient descent, and it actually is often called generalized gradient descent. Just a few years ago when I had these slides, I was calling it generalized gradient descent, and then it seems like the trend had changed. Everyone was calling it proximal gradient, so I just changed everything in the slides to say proximal gradient. But I used to call it generalized gradient descent. And I think this is a nice name because it reminds you that actually this is a generalization of many cases of gradient descent type algorithms that you already know. So let's look at all the special cases that we get out of proximal gradient. So when h is 0, we just get back gradient descent. Right? This is exactly gradient descent. Why? Well, when h is 0, if we go back to this algorithm, when h is 0, what is the prox operator? The prox operator is just the identity. You pass in x, it gives you the z that minimizes this criterion, and that is x. When h is 0, the z that makes the smallest as possible is just x. It doesn't depend on t. Right? The prox operator is just always the identity mapping, which means that we're just doing gradient descent on g, right? Because this prox is just giving you back what you pass in. So it's giving you back x minus tk times grad g. And that is just gradient descent because when h is 0, the criterion is just g. So in fact, now that we've analyzed proximal gradient, now that we've come up with a method for backtracking for proximal gradient, we've actually kind of redone all the work we did 3 lectures ago for gradient descent. I mean, we have strictly more, but we've kind of reestablished all those same results that we already had, right, in terms of convergence, backtracking and its convergence, etc. So it's a nice generalization of gradient descent. When h is the indicator function of a convex set C, then we get projected gradient descent. Okay, it's because the prox operator in this case is the projection onto C. We'll just go through that in just a second. And when g is 0, we get something called the proximal minimization algorithm. So this is when you have only, let's say, a non-smooth but convex function as your criterion, whose prox is kind of more or less tractable. It's an alternative to the subgradient method. And all of these algorithms have a 1 over epsilon convergence rate. We know that because proximal gradient does. Right? So we kind of automatically know what's going to happen for all of these algorithms. So let's do the projected gradient descent case first. So if we have a convex set C, and here I'm saying it should be closed to, so the projection is well defined, then minimizing g over the set C is the same thing as minimizing, of course, g plus the indicator of C. Seen this trick several times. And the prox operator, right, if we call this g and we call this h in our usual notation, the prox operator of h, this indicator function, is nothing more than just projection onto the set C, right? Because it's the same trick we used up there. If you want to minimize 1 over 2t times the L2 norm squared of x minus z plus the indicator of C at z, it's the same thing as minimizing just over z in the set C of this part, right? 1 over 2t times x minus z squared. But of course, the 1 over 2t doesn't matter here, right? Because once this is the criterion, we can scale it however we want. So it doesn't depend on these step size. So in this case, the prox operator is just the projection operator onto C. So this gives us projected gradient descent, right? Because now at every step, instead of applying the prox operator for some generic function h, we can think in this particular case as we're applying the prox operator for the indicator, which is just projection onto the set C. And another kind of nice thing that falls out of this that tells us that if we do projected gradient descent, if we have constraints and we want to minimize a smooth convex function over constraints, we can do projected gradient descent, and that still has the same convergence properties as gradient descent, right? Because it is a special case of proximal gradient, and proximal gradient has those convergence properties too. So take the gradient step with respect to g, x minus t grad g, and then project back onto your constraint set. Picture is kind of something like this, right? Suppose we're trying to minimize, in this case I have a quadratic, and I have, this is my constraint set in 2 dimensions. Okay, it's like a diamond. And these are contours of my function g, and this red diamond is my constraint set. And let's say the global minimizer, if I was not worrying about the constraints, is here, right? That's where it would be. So what projected gradient does, right, is at every point, we take a step with respect to the negative gradient of my function. So move orthogonal to kind of the contour that we're sitting on right now towards the global minimizer. And then, well, this isn't feasible anymore, so we have to project back onto the constraint set. Okay, and here actually this looks like it is the solution, right, because this is where the contour touches the constraint set. So, or at least we're very close to the solution here. So that's nice, because now we know how to do, if we know how to do projections, we can do, for a particular set C, we can handle smooth minimization over C, just with projected gradient. Okay, the other special case is called the proximal minimization algorithm. It's not really very widely used or very widely taught, because it's not often that we know that kind of the functions that are convex but non-smooth are kind of amenable to this kind of algorithm, because we don't always know their proxes. But if we did know the prox of some non-smooth convex function, then we could do something called the PMA, proximal minimization algorithm, which just repeats over and over again application of the prox. Right? That's because when g is 0, where we would usually have x minus t grad g here, we just have x. So these are the updates. Apply the prox over and over again. That's it. It's faster than subgradient method. We know it converges in 1 over epsilon, on the order of 1 over epsilon iterations, but it's not usually implementable unless we know the prox in closed form. Right? So there's some very old classic literature on this, but I don't think people really tend to use it much anymore. Yeah. Yeah, it's a good question. I think that with proximal minimization algorithm, you can kind of do things akin to what you do for the subgradient method, so diminishing or fixed. I don't know that the usual rules would make sense here. So, yeah. I really don't know of very many cases where this is used either anymore, but it's just kind of maybe something to point out that this is an algorithm that in principle has fast convergence, but it doesn't really have a lot of applications, because H has to be quite simple in order for us to want to use this, right? And H is the whole criterion here, whereas opposed to before, it's just part of the criterion. Okay, let's see. Great. So we have one more kind of bit on proximal gradient, then we'll take a break and then come back and do acceleration. So the last thing I wanted to talk about is what happens if we can't evaluate the prox. This is a question that I think people encounter all the time in practice, which is that they have a problem and they want to run proximal gradient, but they don't have exactly the one norm, they don't have exactly the trace norm, they don't really know how to evaluate the prox, but they have an algorithm to kind of approximately evaluate it. Okay, they can actually treat that maybe, say, as a separate minimization problem and iterate a bunch of times just to get a solution to this problem. And they ask, well, is that good enough? Can I actually use that, say, inside proximal gradient? Will that converge? In general, it's not clear what's going to happen if you approximately evaluate the prox. Okay, especially if you're not kind of getting very accurate solutions. There is some nice theory that shows that if you can kind of precisely control the errors in approximating this prox operator, then you get basically all the same guarantees that you get with proximal gradient. That was kind of recently established. You can take a look at, say, this paper. That's called the inexact proximal gradient method. It's inexact because the proximal operator is not exactly evaluated. But what's required by this paper is that the errors you make in evaluating the prox kind of diminish over the course of the algorithm. So as you keep running the algorithm, as you get closer and closer to optima, you actually get more and more accurate proximal evaluations. So that means if you're running something iterative, you have to kind of run more iterations each time each step in proximal gradient, you have to run more iterations in this inner loop just to somehow get an even more accurate approximation to this actual prox. So it maybe is something that you have to just be very careful of and aware of in practice. If you're just evaluating this roughly and you're not kind of increasing the accuracy over the course of proximal gradient, this may diverge. You know, it's not uncommon to see cases in which if you just really roughly evaluate the prox, it's going to diverge. Okay, so just maybe have that in mind and check out this paper if you want to see kind of the exact statements. Okay, let's take a break and then we'll come back and do acceleration. Let's jump back into it because you guys are going to have to learn acceleration in the next 20 minutes, which is possible. I mean, this is all it is right here. But it has kind of a neat history. So let me spend a couple minutes talking about the history, and then we're going to explain what it is. So we mentioned when we covered gradient descent that actually it wasn't getting what we thought was the optimal convergence rate. Right? It was getting a 1 over epsilon rate, but somehow there was this conception that it was possible for first order methods to get an even faster rate, 1 over the square root of epsilon. That came from this theorem from Nesterov. And in fact, Nesterov has 4 papers starting in 1983 and going all the way through 2007 that explain really 4 different ideas for how to accelerate basic gradient methods. And they're just, I think, really kind of unbelievable papers in terms of the amount of ideas they put forward. And it's really, I think it's really changed a lot about how people view first-order methods. The fact that also we can achieve the optimal rate, I think, is pretty interesting. And it has big practical consequences because we're going to see, and you're going to see in your homework, that acceleration can really help speed up the convergence of first-order methods. So here are the papers that I'm talking about. If you're interested in this kind of progression of ideas across the years, take a look at them. They're all, I think, fairly readable. What we're going to talk about today is actually kind of a version of acceleration that comes from this paper, Beck and Tabboul, which really took Nesterov's 1983 idea and applied it to composite functions. So back in 1983, Nesterov had this original acceleration idea for smooth functions. So he was talking about accelerating gradient descent. He wasn't talking about proximal gradient. And what Beck and Tabboul did in 2008 is basically took this idea, and it's a very nice treatment of it, and applied it in the proximal gradient setting, which is what we'll talk about today, because it's kind of the most general way to look at it in some sense. Okay, so our setup is the same as before, G plus H, G convex and smooth, and H convex, but not smooth, but we know it's prox. And we're going to learn something called the accelerated proximal gradient method. And it has kind of 2 steps per iteration rather than proximal gradient, which only has 1 step. And so here's the way we look at it. We choose 2 initial points, x0 and x minus 1, and it's really kind of commonly just a common set is equal to the same thing. So just pick some initial point like we do in proximal gradient, say 0, and then define a x0 and x minus 1 both to be that initial point, like 0. And then repeat. So first we derive an intermediate variable, which is given by what's called applying momentum to the point xk minus 1. So at the first step, actually, at x, when k is 1, right, these 2 are the same. This is x0, this is x minus 1. So this intermediate variable v is just x0. Okay, there's no momentum being applied whatsoever. So we're really starting off the algorithm in the same way that we did with proximal gradient. But every step after that, okay, this difference is not going to be 0. And what we're doing is we're at xk minus 1. Okay, and let's say we were at xk minus 2 in the previous step. And instead of taking a gradient step from this point with respect to g, right, looking at the gradient of g at this point and asking us where it's going to direct us, taking a gradient step and applying the prox, we use what's called momentum, which is that we look at the direction from xk minus 2 to xk minus 1, and we let that kind of continue to push us. We let ourselves to be pushed in this, continuing in this direction before we evaluate the gradient of g. Right, so we take some multiple of this and we add it to xk minus 1. Now we evaluate the gradient here. Okay, instead of evaluating the gradient here. And we take a gradient step with respect to this point, which we're calling v. Okay, so I take xk minus 1, I add on some multiple, okay, and in fact, this is a prescription that will give us kind of nice convergence. K minus 2 over k plus 1 times the direction pointing from xk minus 2 to xk minus 1. Then I take a gradient step with respect to g at that point at v, and I apply the Prox operator. Okay, repeat that over and over and over again. So let's just make some notes. I guess I already kind of said all this. The first step is just the usual proximal gradient, because xk minus 2 and xk minus 1 are the same thing when k is 1, right? Usually by construction we make that true, so that it starts off just like proximal gradient. After that, we carry some momentum over from the previous iterations, right? We try to let ourselves be pushed along by a direction that's similar to the direction we've been traveling. And when h is 0, if I didn't have a non-smooth part at all, then I just get accelerated gradient method, right? Because this prox is just the identity. So I just get v minus tk grad g at v, and that's just accelerated gradient descent, which is what Nesterov proposed in 1983. Okay. How about these weights? Let's look at what these weights are like. So most interesting, I guess, is how do these look over the course of the algorithm? So here's a plot of just k minus 2 over k plus 1 as k varies, right? K is the iteration counter. So at 1, it's actually negative, but it doesn't matter, right? Because this is 0. When k is 1, the direction is 0. So it doesn't really matter what that weight is. As the algorithm proceeds, you can see that these weights get closer and closer to 1, right? Which means that we're applying more and more momentum, right? We're asking ourselves to be carried forward more and more by the direction of previous iterates. So why is that a useful strategy intuitively? Why is it useful to have more and more momentum as the algorithm proceeds? Why do you guys think that's the case? Think about gradient descent when h is 0. What do we know kind of about these steps as the algorithm proceeds? They're getting smaller and smaller because the gradient's getting smaller and smaller, right? So what is it meaning to have kind of momentum, more momentum later on? It's kind of pushing us farther at the time in which we take smaller and smaller steps, right? When we're closer to the solution, when we usually were taking smaller gradient steps, smaller steps effectively because the gradient is smaller, this is asking us to be, this is having us kind of carry more and more momentum in terms of allowing ourselves to be pushed in the direction that we've been going so far, which is what we want to be doing, right? If we're close to the solution, presumably the directions we've been moving are good directions, right? We're getting closer to the solution. So it's exactly the right time, in a sense, to be applying more and more momentum. So that's why I think this trend makes sense, right? These weights get higher as the algorithm carries on. So let's just do an example. So here's an example. Remember, I already showed you this picture. I had subgradient method for the lasso. I was in black. I had proximal gradient, which appeared to be, creaming subgradient method in terms of the convergence, empirical convergence here, and also theoretical convergence. This is 1 over epsilon squared. This is 1 over epsilon. And now we're here. Okay, this is what we got with applying acceleration to this problem, to the lasso problem. And in fact, it's no more expensive computationally than proximal gradient, really. It's essentially the same complexity. So again, a fair comparison, and again, a much faster convergence. And this guy, as we're going to claim in the next few slides, is indeed at the optimal rate. This is 1 over the square root of epsilon. Okay, so among first-order methods, this is about as good as we can hope for in terms of convergence. So if you look really carefully, I guess I don't have this zoomed in. If you look really carefully, you can see that the criterion does not actually decrease monotonically. It turns out that acceleration does not provide you with a descent method. That's why I've called this the accelerated gradient method rather than accelerated gradient descent or accelerated proximal gradient descent. Okay, we're using the word method instead of descent. If you look very carefully, we don't get monotonic decreases in the criterion value. And in fact, if we were to somehow stretch this out and blow it up, you'd see you get these kind of characteristic ripples. Some people call these Nesterov ripples, just kind of in honor of Nesterov. That's what it looks like when you run accelerated gradient method or accelerated proximal gradient method. So the convergence analysis is not something we're going to do. It's possible to do in class. I think maybe the first year I taught acceleration, we did the proof in class, but it is more sophisticated than the proof for gradient descent. It requires just a little bit more careful numerical analysis. But so if you want to, you can look back at the slides for previous iterations of the course, or take a look at this paper. This Beck and Touboul paper has a very, very nice presentation, I think, for the convergence analysis. But here's the statement, at least. If we have the same setup as we've been considering for proximal gradient, right, g plus h with g smooth and convex, and grad g Lipschitz, and the prox function of h being tractable, then if we take a fixed step size, okay, that's anything less or equal to 1 over L, then we get a very similar result that we got for, in some sense, for proximal gradient, except with the key difference is that k in the denominator has been replaced by k plus 1 squared. So it's 2 times the square distance between x0 and x star divided by the step size t times something like k squared. So in epsilon notation, that means if we want to make this less than or equal to epsilon, we only need on the order of 1 over the square root of epsilon iterations rather than 1 over epsilon iterations. Okay, these 3 rates, they actually can make a big deal in practice. Okay, especially if the algorithms that you're talking about attain these 3 rates having similar per iteration complexity. Right? Just think about epsilon being a small number like 10 to the minus a third. Think about if we're asking for 1 more digit of accuracy, how does that inform us that these methods should scale in terms of how many more iterations we need? Right? So subgradient method, gradient descent, and proximal gradient, and then the accelerated versions. Backtracking with acceleration is possible. It's a little bit more tricky than it was for proximal gradient even. And one difference, I'll just leave it up on the, I think I won't probably go through this carefully because, yeah, but I don't know how much we gain out of kind of going through the difference in this exit criterion and the proximal gradient exit criterion, but the details are all here. Okay, it's just applying to g like we had for proximal gradient rather than checking a descent on g plus h. One important difference that people sometimes miss, which is potentially a reason sometimes that backtracking will not converge for them for accelerated methods, is that here, when we run backtracking with accelerated, say, proximal gradient, we actually have to have the step size, t, that we start off with before we run backtracking, set equal to the value that we quit on at the last backtracking cycle. Okay, so usually in proximal gradient or just in gradient descent, we're allowed to start at any big value we want, right? We can start, say, at t equals 5. We can always try taking a step size of size 5. That doesn't work. Let's make it smaller. In accelerated methods, we are required to kind of always make the step size smaller as the algorithm proceeds if we're going to be using acceleration. Or at least this is the version for which we have guaranteed conversions. I think there are several other kind of alternatives to backtracking under acceleration, and they probably can get much more complicated than this, but here is a simple enough version that we know converges. Okay, and like backtracking for proximal gradient, we have to evaluate the prox at every inner loop of backtracking here as well. So under the same assumptions as we had for accelerated proximal gradient with a fixed step size less than or equal to 1 over the Lipschitz constant, we get the same rate. Okay, so backtracking does it for us too. We get the optimal 1 over the square root of epsilon rate. So I guess I just have, let's see, yeah, a couple more things. FISTA, which is the accelerated version of ISTA, and then just taking a step back and talking about when acceleration is useful and when it may not be as useful. So for the lasso problem, remember we had this algorithm called ISTA, which we derived just by using proximal gradient. Stands for iterative soft thresholding algorithm. If we apply acceleration to proximal gradient and then see what that looks like for this problem, we get something called FISTA, or at least that's what it's called in this paper, back in Touboul, where the F stands for fast, the fast iterative soft thresholding algorithm. And it's just the usual kind of formulation of acceleration here, right? We take our coefficients in our lasso regression problem. We apply a bit of momentum to move us in the direction that we've been going so far. And then we add step size times the gradient of our loss function, or subtract a step size times the gradient of our loss function at this intermediate iterate called v. Okay, so we take v and we add a step size times the correlations between all of our variables and the residual, and we soft threshold that. That's the FISTA algorithm. Repeat this over and over again. And you can see this is no more expensive than ISTA, right? This step does not really add any computational complexity at all. It's nothing. And that was the guy that had much, much faster convergence. So here I had an example of, I ran this for 100 different instances. So I generated 100 different problems with kind of a random design and random response, just to kind of show some variability here. And this is what the convergence looked like for FISTA and ISTA when they were both kind of tuned to have the largest fixed step size possible before they diverged. Okay, so this is supposed to be representing kind of ideal convergence behavior for both of them. And we have much faster convergence with FISTA. This is the average convergence rate here in the dark blue and the average in the dark red. And in fact, every instance of FISTA was faster than every instance of ISTA, right? They don't even cross. So this is really a lot faster. And then it's the same for logistic regression. I just changed the problem a bit to try to convince you that this wasn't just to do with the lasso with the square loss. For logistic regression, again, they're no more expensive one versus the other. They're both pretty cheap, but FISTA is just much, much faster. So let's just finish on a few thoughts about, is acceleration always useful? Some people see acceleration and they see how fast it converges and they see the optimal rate, and then they just think, okay, whatever I'm doing, I'm going to accelerate because it must be worth it. And there are cases in which it's really helpful, like these ones that we've seen, but there are cases in which it's maybe not worth it, or even it can actually be harmful, in the sense that it can just kind of introduce additional complications into your iterations. And here's one situation in which it's usually not worth it. It's not harmful, but it's often not worth it to apply acceleration. And that's in a situation in which we want to solve a sequence of lasso problems, let's say, or a sequence of convex problems, where we're just changing something like a hyperparameter that's multiplying one of the terms in the criterion. So for the lasso, let's think about, we want to solve a sequence of lasso problems at different values of the tuning parameter lambda. In this case, what we almost always do is use something called warm starts. Okay, and we probably will talk more about this as the course continues on, but we actually sort the values of lambda that we're at which we're asked to solve the problem. We solve the problem at the largest value of lambda, and then we record that solution. Let's call it x hat of lambda 1. And then in order to solve the problem, say at lambda 2, instead of initializing our proximal gradient algorithm at 0, or at some random guess for x0, we initialize it at the solution that we found at x1. Okay, that's called warm starting. It's putting us in a good spot. And the reason that's useful is that the lasso solution, as a function of this hyperparameter, this tuning parameter lambda, it actually behaves continuously. So as you move lambda a little bit, the solution itself only moves a little bit. And that means it's actually a good idea to be starting us off for, say, a slightly smaller value of lambda, starting our algorithm off where we converged for the previous value of lambda. When you do this, if you do this strategy called warm starts, first of all, it means that the number of iterations that you actually see as the kind of sequence of lambdas, as you travel down the sequence of lambdas, it's far, far fewer than what you'd see if you just picked, say, a small value of lambda to begin with and tried to solve the problem there. This warm starting really speeds up the convergence in general. And given that it's doing that, it's often not useful to apply acceleration. It doesn't hurt, but acceleration doesn't really buy you much in many cases when you're already warm starting. Okay, and this is pretty common in many statistics problems to want to solve, say, an optimization problem over a sequence of hyperparameters. So that was an example where it's maybe it's not worth it to implement acceleration. Here's an example in which actually it can hurt, and that's the matrix completion problem. So the reason why is somewhat subtle, but it's also important because this kind of thing can happen. That certain formulations of algorithms are really efficient because we can do something like their prox operator efficiently. If you try to apply acceleration, then it messes that up and the iterations become much more expensive. And matrix completion just happens to be an example of this. So remember that in matrix completion we needed to do something like an SVD to compute the matrix soft thresholding operator. And what I had argued was that actually when t is 1, okay, if we use a fixed step size of t is equal to 1, then that was actually pretty efficient because what we were taking the SVD of was a sparse plus low rank matrix, and there are fast algorithms for that. If instead we decided to do backtracking, that would actually be bad here for matrix completion, because every iteration of backtracking would require us to evaluate the prox, which is a full SVD. So already backtracking is super expensive. And more so than that, when t is not 1, if we're doing backtracking and playing with a step size, we don't have that nice sparse plus low rank structure. Okay, at least it's not, it's not clear that we have a structure that's amenable to fast SVD computation. The same is actually true with acceleration. If you go through and you ask, what is the variable at which we're going to be applying the prox in proximal gradient and in accelerated proximal gradient, you can see that in proximal gradient, it's essentially always we're applying the prox to this guy, which is a sparse plus low rank matrix, which is what we'd seen. And in accelerated proximal gradient, even if you had a fixed step size for matrix completion, it's actually a sparse plus a not necessarily low rank matrix. So this guy here, wherever we'd written this down here. So if you apply this step, right, to replace beta by a matrix B, this thing may not be low rank anymore. Right? We're taking linear combinations of matrices that may actually not have the low rank structure that we want. So it's not as easy to do the SVD to call the prox operator at the point V. So actually, you can check out that soft impute paper. I think they actually have examples in which acceleration provides you with a slower algorithm, because each iteration is actually much slower than it would be for just the usual prox gradient. Okay, so think of acceleration as a very useful general tool, but not like an all-purpose hammer. There are cases in which it maybe isn't worth it, and you have to just kind of think about it on a problem-by-problem basis. Okay, that was it. I guess I will see you guys on Monday.